All right, so let me give you a couple examples. And these are literally just straight up, I want to see if I can spot the problem spots. So here's a differential equation. Y of x is x squared minus y squared over x squared plus y squared. What I am trying to spot is this kind of funny question of where is the rectangle not? Like, in other words, which points in the plan which points in the plan do you have to avoid with your rectangle to be able to say something about existence in uniqueness?
Avoid the origin.
Yeah, you definitely have to stay away from 0 on this one. You guys see that? Okay, so if your rectangle doesn't contain 0, 0, you can play existence and uniqueness games. Right? You can know that your solution exists and is unique, at least on some little subinterval. If your rectangle contains 0, then you're dormant.
Would that just mean that we can't know, but there might actually be one? But we don't know for sure?
Yep.
Or there is none?
No, you don't know for
Okay.
sure.
Okay. It's kind of like the...
Yeah, we don't have a not-existence theorem either. We only have an existence and a uniqueness theorem. We don't have a not-existence and not-uniqueness theorem. So this thing is like a pretty weak tool. Right? This tells you, yo, you should probably stay away from 0.
1 would be a problem too, right? You get a 0 in the numerator.
You need to get 0 slope.
Yeah, 0 slope. Like 0 slope happens. Right? Sometimes it's even interesting. How about another one? So what if I had y prime is, say, I don't know, x plus y over x minus y.
X and Y cannot be equal.
Yeah, it seems like x and y can't be equal, right?
So avoid the line y equals x.
Yeah, avoid the diagonal. Cool with that? Does that make sense? Like, just if you tried to use whatever technique to solve this thing. Do I have a technique for this?
Solve a differential equation.
Yeah, to solve this guy.
It's not linear.
Good, it's not linear, because if you multiply, right? So you need to get y prime, maybe times a function of x, plus some function of x times the y's equals some other function of x, right? For it to be linear. I think you got a y and a y prime tangled up here.
You can use a field to evaluate approximately.
Yeah, you could try to numerically approximate by like making a slope field and try to run some solutions around that way. You could try some other stuff that we've talked about. But if you found a solution on this, you would know at best that you have to stay away from the line y equals x, right? You definitely can't cross the line y equals x and expect for that solution to still work. Is that a huge surprise? No, it's where you're dividing by 0. Don't be crazy. You can't go over that. Right? Let's see. So, an example of the uniqueness part. What if I had y prime is, say, 4xy? First, what's your function of x here? Wait, f. What's your f for that, our existence in uniqueness?
F?
Yeah. What's f?
F of x and y?
Yeah, f is a function of x and y, and it's 4xy, right?
That's a linear homogeneous.
Yeah, that's.
Oh yeah, we can solve this. The reason I wanted to demonstrate this is we can solve this,
Okay.
right?
Okay.
So I want to talk about what we know about the solutions before we go there.
Okay.
So if my f of x and y is 4xy, what is that function continuous?
Yeah.
Yeah? It's a polynomial in x and y's, right? In fact, it's a monomial in x and y's. Probably continuous. What's fy of x and y? Just 4x, right? Is that continuous? Totally. Cool. What do I know?
Unique.
Yeah, I know that if there's a solution, it's unique. Because f is continuous everywhere, I know that if I had any particular initial condition at all, there would be a solution at least locally. And I now know that that solution would be unique, at least locally.
So there's still an infinite number of solutions to that with some constant thing, but if we pick,
Yeah, if we pick the constant, then we know that there's no branching. So let me hit you with what we know about this thing. My claim is that you know that the solution to this is either y is identically 0 or y is some stuff.
so like, as I was saying, like, we won't get like, if we pick one of the constants, we're not gonna get like y equals 2x and also y equals negative natural log of x.
How about specifically, y can't be identically 0 or also be this stuff, right? You guys see that? So if y equals stuff hits 0 ever, then it would be always 0 because the solution's unique. You guys see that? So I know that the solutions I get out of this should either be identically 0 or should never be 0. Right? What's the solution you actually get out of this? What's your y? You guys can solve that.
A e to the negative
A e to the,
negative 2x.
George Sparks? Is that ever 0?
Well, what if you make a equals 0?
If you make a equals 0, then you're here,
Yeah.
right? And if a is not 0, then this thing is never equal to 0.
But it's one or the other.
Oh, cool. But it's one or the other, right? Like either it's always 0 or it's never 0. And the reason for that is that I know the solution's unique. So if it's ever 0, then it satisfies the same IVP as the identically 0 solution. And then there's only one solution to this thing, so it would have to be identically 0.
Will we ever have trivial solutions that are not y equals strongly 0?
No, that's what a trivial solution is.
Okay.
Okay, cool with this? Questions then? That help kind of nail down what, like the existence thing is actually more useful to me than the uniqueness thing is more useful to me as a human being than the existence thing. The existence thing is nice if you're trying to do numerics. Because if you know there's some solution, then it makes sense to go hunt around for it. If you're not guaranteed uniqueness or existence at all, you could be really wasting your time looking for a solution. If you're not also guaranteed uniqueness, if you find a solution, it might not necessarily be good for anything. You guys see that? Like, sure, it solves your differential equations, but does it predict how something moves in the world? I don't know, maybe not. Maybe the other solution that you didn't find is the one you wanted. You guys see that? They actually spent a bunch of time wondering about Navier-Stokes equations. Like, we're not sure about those. It's a cool thing. Mathematicians would like to say something like, obviously the Navier-Stokes equations have unique solutions that exist everywhere, given reasonable assumptions. And we're just not quite there yet.
Navier-Stokes equations?
Yeah.
Is it class?
Navier-Stokes models how gas moves. So like the fluid flow equations, basically. There are some weird spots that seem like they could possibly cause things to act in strange ways if you set the viscosity basically to infinity or set densities to weird things like There's some strange stuff that could happen.
Was that the same guy who has Stokes theorem?
I believe that's the same Lord Stokes, but
Green theorem also?
So is it like
Same
11?
thing?
Green's theorem is similar to Stokes. Green's theorem is a corollary to Stokes' theorem. But Stokes' theorem is not explicitly used in the Navier-Stokes equation.